with circuits, and we started with our little summary. Something I forgot in your summary. So just somewhere, I think on the last page, something I forgot in your summary was your cells, your battery. The long one is positive, the short one is negative, and your cells are your home, or is your home. Whatever, it's home, where you get your energy. Energy is gained at home, hopefully. Yes? No? Some people. All right. So we spoke about the ammeter being a register that measures how many charges pass there per second. We spoke about the volts, that is your it measures the potential difference. It measures where energy is used or energy is given. Okay, and then we said that is Miss Phsc, so she checks your energy levels. Are you all right? Then we spoke about your resistors, that is your subjects or your period that takes energy. Okay, then I wanted to draw a small circuit just to recap how this works again. Please, this is not art class or EGD. It's just a quick drawing. Do you know it's EGD?
Yes. But we don't have to.
What is EGD? IGO, it's hoe would it? Engineering, graphic and design. All right, let's say in this circuit, this is English, this is, yeah, let's make it math and math lit. Yes. Okay, there can be voltmeters, but remember, voltmeter does not have to be a permanent thing in a circuit. Okay, so here you walk with your sandwiches. How many you here have? You see that everyone passes through that ammeter, so that ammeter measures the total current. Because everyone passes through it, so it measures how many charges pass there per second. Then you see that everyone needs to pass through English. And then the current, the little men will split up. Some will go to math and some will go to math lit. Will they split up equally? No, we don't think so. We think that more people will go to math lit because it's easier. It's less resistance. So the current here will be bigger than the current there. So we can say from there that current is inversely proportional to resistance. The bigger the resistance, the smaller the current. Rings a bell? Okay. Then they all get together here again and they go back home. Okay, now if you plan, you are one of the little men that walks in the circuit, if you plan your sandwiches, your energy for the day, then you say, all right, I have to go to English or math, or English or, not or, English and math, or English and math lit. You don't say English, math and math lit, because you're not allowed to go through there and back there. Okay, so when you plan for the day, you only plan to go to 2 subjects, so you've got to split up your sandwiches into 2. Your energy, you split up. You might split them up equally. We don't know. We'll have to get to the resistance and. But what we do know is if you take math or if you take math lit, you get the same number of sandwiches. Just because you take math, do not mean that you get more sandwiches. Okay. Sharp, sharp. Now I'm back in your notes. I think we're on page 2. Okay, I'm going to go through electrical current again. What is that? So electrical current, the symbol for that is capital I. That is the amount of charge, Q, that flows past a point per means divide by, seconds, the time. So the current is the amount of charge per second. Okay, so it's just that formula that is rearranged. Yes? Okay. This is all grade 10 work that I'm quickly revising. Then we are at electrical potential energy difference, or potential difference, PD. And it says there, potential difference between 2 points in a circuit is the quantity of work done or the energy transferred per 1 coulomb charge which is moved between the 2 points. What's wrong? Oh, are you one of those people? I get the same, but I'm not that sensitive. Alright, so what does this mean? The quantity of work done or energy transferred per 1 coulomb charge. It is, there at the bottom of the page, you should have a bit of space. Okay. Let's say that is math. And let's say Ms. Phsc, the voltmeter, takes your energy levels before math. Let's say before math you had 5 sandwiches and after math you have 2 sandwiches. Then what does that voltmeter do? It measures the potential difference. Your potential was 5 there, the potential is 2 there, so the potential difference is 3 volts. Okay, so what does that mean? What's wrong? Okay, so what does voltmeter do? It measures the potential difference. Difference means final minus initial, or the difference between the two. So let's say before math you had 5 sandwiches, after math you had 2 sandwiches. What is the difference between the two? 3. So that is what a voltmeter measures. So what does this mean, this 3 volt measurement? What does it mean? It means for 1 coulomb, for 1 man walking, it takes 3 sandwiches to pass through math. So each man needs 3 sandwiches to pass through math. So it means, I'm going to read the definition again. The quantity of work done or the energy transferred. How much energy is transferred per 1 man walking through those 2 points? From this point to that point. Okay, so you can see the quantity of work done or energy transferred means the same thing, because work done or energy transferred are both measured in joules. Okay, so work done or energy transferred are both measured in joules. Can I go up? Potential difference is measured in volts. And then Q is your quantity of charge. So if we have, for that scenario there at the bottom, if we have 4 charges, how much energy of joules or joules will we need? For 1 charge it was how many sandwiches? 3. So for 4 it will be 12. You get the concept. Alright. Then it says there, potential difference is only exists in a circuit where energy is added. So in a cell you can measure it, or where energy is used. Okay? I'm going to go back to my scenario here. I'm going to draw a very funky circuit now. They say there must be another something there. I don't know what. Unknown. Okay. If I put a voltmeter here, what will the reading be? Carabello?
It's going to be 5.
Ah, Karamu, sorry. Oh, why 5? You're right. So you see, you started with 5 here. Something is going to use 2 sandwiches. That's something we don't know what it is. We don't care. But when it goes back home, it has how many sandwiches? 0. When it leaves home, it has 5 sandwiches again. So that difference between them is 5. Okay, so the cell adds energy, and because it adds it, we can measure how much does it add, the potential difference. If I put a voltmeter here, what would the reading be? It comes with 5 sandwiches there. Did it use anything?
No.
So it has 5 sandwiches. So what's the reading? 0. Because remember, it measures the potential difference. Did we use any energy? No. So it won't help to put a voltmeter over there because the difference is 0. Chop, chop. Okay, so that is what it's meant here. You can only get a potential difference if you add energy or if you use energy. In the middle where you don't add or use, then you'll get no reading. Okay, then they say potential difference is measured between 2 points in a volt or with a voltmeter connected in parallel. And then a voltmeter has a very high resistance. Why? Why does it have a high resistance? We said the previous time we said an ammeter has a low resistance because it's register. You must just pass through it. It shouldn't take any energy. A voltmeter has a very high resistance. Hoekom? Say again, Florna? No. Does Miss Phsc take your sandwiches and when she looks into your bag she's like, oh, one for me, one for you? No. It measures the energy, yes, but that is not block. Yes, but no, you're not answering my question 100%. Say again? The energy must go through the voltmeter. Energy does not move through. You do not want the circuit to split up. You don't want some people to pass through Miss Phsc and other pass through the wire, through the corridors. You can't pass through her. Okay? She is just an outsider, quickly measuring here and measuring there. You do not want your circuit or your current to split up into 2. So what they do is they make this resistance very, 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 very high, so that if for some reason the chargers would want to go through there, they can't. It's impossible. It's a closed door. They must turn back and everyone must pass through there. All right. Okay, let's look at an example there. So calculate the potential difference across each resistor in the circuit. Okay, now here you see the positive side, that's the negative side. You start with 24 sandwiches. There you walk. Do, 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 do. So before that 9 ohm resistor, let's start somewhere. Montle, how many sandwiches do you have in your bag? 24. All right, I'm going to tell you what do you have left afterwards. You have left 6 sandwiches. Okay, I'll show you now 2 ways how do we get to 6. Then you walk with your 6 sandwiches. Do. Dimakato, how many sandwiches do you have before the 3 ohm? No calculation needed. 6. Okay, and Orifulwe, how many do you have afterwards? Say again. Where do you go after the 3 ohms? And are you allowed to go home with food in your bag? No. So you have 0 sandwiches left afterwards. Huh? How what? You're definitely not going to say 6 minus 3. No, because that is 6 volts. Oh, this is just a normal bell. This is 6 volts. This is 3 ohms. It's two different things. Can I say you have 3 bananas plus 3 eggs? Now you have 6 eggs. No. It's two completely different concepts. So look at the units. This is volts. This is ohms. You cannot add or subtract. You can divide and multiply to get into the equation, but you can't add or subtract it. Okay, right. Now, how did we get to that? There's 2 ways. Are you just tired today? Well, okay. All right. So, we want the volts. But to get the volts, we must first get the current. Okay? And for that, we need the resistance. And then we can get the volts. Now, the total resistance in that circuit is what? 12, right? They're in series with one another. 3 plus 9 is 12. The total volts in that circuit is 24. Okay, so to get the current, it's going to be volts over resistors. That is 24 divided by 12, and that gives you 2 amperes. I'm doing this very quickly because we're going to practice that again, and it should be easy. Ish. Okie dokes. Right, now we want the volts. Let's say we want the volts. Let's say voltmeter V1. Okay, so I want V1 is current times resistor. The current through it is that 2 amperes because the total current passes through it. And the resistor that V1 measures is for the 3 ohms. Times 3 gives you 6 volts. Okay, so you can see there 0, 6, that is 6 volts. Without doing a calculation like this, but using this information, what will the voltmeter reading be there? Say again? V2 will be what? How did you get to 18? Okay, but I say without a calculation like that. Okay, let's, yeah? No? Okay, I'm going to explain my sandwiches story. You walked with 24 sandwiches. How many periods did you have for the day? 2. There and there. Here we figure out you used 6 sandwiches. What is the reading here? No. You have 24 sandwiches in your bag. You already ate 6 there. Then you have 18 left there. Okay, so you are going to say 24 minus 6 gives you 18 volts. Okay, remember this is just a recap. We are going to do it again. Don't stress too much just yet. Okay, then there's another way to do it. The other way is ratios. Alright? What do you do with ratios? You look at your resistors. I have a 3 ohm resistor and a 9 ohm resistor. So you write for yourself 9 and 3. 3 and 9. Together, they give us 12. Right? Okay, so we have 3 over 12 and we have 9 over 12. Of what? Of. Okay, what is the question? The potential difference of the volts, of the total volts, of 24. Does what? Without a calculator. Yes? I know you can do it. That means divide by. Yes? 24 divided by 12 times 3. There you go. And the other one?
80.
Mine mag is, because you should. It's the same question. Alright, so what does that mean? Through the 3 ohm resistor, the volts is 6. And through the 9 ohm resistor, the volts is 24. The volts is 18. Okay. And there's something I wanted to say here. You can only do ratios if there's 2 things that you compare. As soon as there's 3 resistors, you can't do ratios anymore. Okay, only when there's 2. But ma'am, parallel, they will have the same voltage, but they will have different. Same potential difference, different current. Then you can do it again with current. Now, I don't know, some of you, maybe you remember this of last year. Ma'am, didn't we last year say this belongs with this and this belongs with this? Yes. When did we do that? We did that when we were busy with current. Okay, I want to prove to you why this belongs to this now. What did we compare? We compared volts and resistors. Resistor 3 ohm with volts. Yes? Okay, if you look at this formula, you can see that volts is at the top, resistance is at the top. The same current passes through both. Yes? So the current is constant, so we can take that out. So from here, we can say that volts is directly proportional to the resistance. Meaning, the smaller resistor has the smaller volts. The bigger resistance has the bigger volts. The thing that you think of is when we compare resistance with current. And then you can see resistance is inversely proportional to current. So if you compare that, then we have to swap them around. Okay, but we are going to practice that again. Okie dokes. Then we are at a new part. So this page 3 is now grade 11 work. You have 2 new concepts in this chapter this year. This is the first one. Okay, Ohm's law. Ohm's law. I think you have also 3 definitions in this chapter for this year. This is the new definition, so this is a one they ask a lot. I'm going to read and then explain. They say, the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. Can you see here that we have 3 variables? We have potential difference, current, and temperature. And remember in science, we can't have 3 things changing. One is our independent variable, one is our dependent variable, and one is our constant. Okay, so they chose to keep temperature constant. But why? Where does temperature come in all of a sudden? Okay? In grade 9, and also a bit last year, we looked at 4 things that influences the resistance of a circuit. The first one was the length. The longer it is, the higher the resistance. Yes? Yes. Then we did the material. Okay, sorry, I wanted to bring it back to periods, the longer a period is, like this period, the more sandwiches you'll need, the more energy you'll need, right? Second one is material, the softness and the hardness of the material. So some teachers are hard and strict, and you feel you can't connect with them, and it's a tough period, and some people are softies, and it's easier in their period, né? But sometimes they're too soft, and then it's also not like that. No comment. All right. Then we have the thickness. Okay, and I explained that last year. I said in the like before rugby match or whatever type of match, then we make a little tunnel for the players to pass through, and we said if the tunnel is too small, then they will collide a lot. If the tunnel is big enough, then they can easily pass. All right. So the thicker the conductor, the less resistance. Okay. So on that note, from grade 10 notes, resistance is the when particles collide. Are you writing? With sides of conductor. Okay, that is what resistance is. How much collisions do you have? Right. Then the last one, there is temperature. The warmer a substance is, let's just go back to, I have something that I can actually show you. Did I show you this the other day? Okay, you can come forward if you want to. Okay, so this is for grade 10 work, but we've got it now. The kinetic molecular theory. So it means when you have a solid, particles are supposed to vibrate on the spot. Liquids are supposed to glide over each other, and then the gas is supposed to be like okay, let's see. Okay, so this is low energy. You can see there's a vibration. And vibration is going to go on there. So this is supposed to be a liquid. Right, and then you put up energy. Right, are you with me? Yes. Okay. So the faster they move, the more energy they have, the higher the temperature. Okay. So with that idea, we can go back. Okay. So if something has a very, very, very high temperature, a lot of energy, then it's going to move very fast, and because it moves very fast, there'll be a lot of collisions, and because there's a lot of collisions, the resistance will be higher. Okay, so we are going to consider for Ohm's law that we keep all of these things constant. We're not changing our wires or resistors, but our temperature we must also keep constant, because if the temperature changes, then our resistance will also change, and we don't want that. Okay, so we want to keep our resistance the same, then the potential difference, so then the volts, will be directly proportional to the current. Meaning, in our sandwiches story, the more energy you have, the faster you will move. Alright, is there anyone in this class that drinks Monster or Play or anything like that? No, and you're all healthy human beings. Or do you drink that?
Yes.
When? You drink it in the mornings? Sometimes. You know, it's like poison in a can.
Yes.
Alright. Okay. Anyway, so let's say Orifilwe drinks them before school, just to wake up, just to like get to school and cope and focus in class. Then she'll have energy. But let's say she drinks 3 before school. then she'll be like on a different level, right? She will like be moving all over the place. So the more energy she has, the faster she will move. And that is what Ohm's law says. The more energy you have, the bigger the current. What is current? How fast they move. Okay, so that is basically this whole law. And the formula that goes with it is this formula that you've been working with since grade 8. No, you did it in technology. Okay. Right. Then I have said this, but I just wrote it down for you. The resistance increases if your temperature increases as well. Okay, guys. So with any law, there is graphs and formulas and. Okay. Now Ohm did this experiment a million times. I just want to get to my notes. Where did I do this? All right. Okay, so you can see here I did two graphs. I have, the one is current versus voltage, and the other one is voltage versus current. So I just swapped the two around. The reason why I did that is they ask both, or they can ask both in the test or an exam. Meaning they can ask you to draw it if they give you the data, or they most of the time they give you the graph, and they can give it other way around. Say again? It could definitely be a multiple choice question like this here at the bottom. Oopsie. But sometimes they give you a graph and you must take the information from there. I think I put it in your notes. No, I didn't. Okay. Right. So, let's look at what this graph gives us. Now, I first want to look at the bottom one. Okay? See there we have voltage on the y-axis and current on the x-axis. You see it gives us a straight line. What does a straight line tell us? Like what mathematical relationship can we get from it? Directly proportional. Now remember we read from left to right. So that is how we read our graphs as well. Left to right. So when we compare our proportionality, we want to compare the y-axis versus the x-axis. That is how we compare. Y-axis versus x. Okay, so this one we're going to say voltage is directly proportional to current. Okay, and for the top one we're going to say current is directly proportional to voltage. Okay, ma'am, it's the same thing. Like, why are you giving us two graphs? You'll see in a moment. Okay, now from these graphs, we can get two types of conclusions, a graphical conclusion and an algebraic conclusion. Algebra means what? Letters, numbers, formula, y, x, b, a, whatever. So graphical means the shapes of the graph. You get a hyperbole, you get a parabola, you get a... Have you started with that? Yes. Okay, you will get to that. Okay, straight line graphs and. So graphical means the shape of the graph. Okay, so let's just write there for yourself. This is the shape, and this has to do with A, B, C, blah, 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 blah. Formulas, equations. Okay, so what I'm going to do, because we have two graphs, let's do this 1 and 2. We're going to compare the two. Like, what is the graphical conclusion for this one, that one, and so forth. Okay, so 1 and 2. The graphical conclusion for the first one, we just did it. We saw that it's a straight line graph. And in science, our mathematical conclusion, let's just say straight. Do you say straight line or do you say linear? Straight line. Okay, both are straight lines. Okay, and from that, the first one we got the current is directly proportional to the volts. And the second one, bless you, we got volts is directly proportional to the current. Okay, then algebraic is formalized equations. Because it's a straight line, we must use the equation for a straight line. Okay, but now we must change this so that it fits our symbols. On our y-axis, for the first one, we have current. Our gradient, we don't know yet. Our x-axis is voltage. And what is C again? And where does it intercept the y? A 0. So it's plus 0. Alright, then you can see I just put in a new step because it's an important step. We want to rearrange that so that we get the gradient of the graph. So we want to get m is equal to, what will it be? I over volts. Okay, then I want to look at the second one. On our y-axis we have volts, the gradient we don't know. The x-axis is our current, and again, I didn't show this now, but it will go through the origin. There's 0. Because if there's no sandwiches, then the men won't move. If they move, there must be sandwiches. Okay, then our gradient will be volts over current. Okay, so what's the difference between the two graphs? Is the gradient. The one is volts over current and the other one is current over volts. It's two different things. If I tell you, you owe me 100 rand, is that the same as saying you owe me 1 over 100 rand? You owe me 1 cent? Definitely not. Okay, so these two things are the opposites of each other, opposites, inverses of each other. Alright, now this looks familiar. This looks like what? The Ohm's law, where we get that the gradient is then resistance. So what will the other one be? The inverse. So here the gradient will be 1 over resistance. Okay, so this is what I want to highlight here. When they give you the graph, be careful. Okay, what does the gradient specifically in this graph give me? Does it give me resistance or does it give me 1 over resistance? So you will do this quick thing where you say gradient is a change in y over the change in x. Yes? And then you'll say, okay, this is current over over voltage, so it's 1 over r. Okay, I showed it there. Okay, so another thing that we can get from this, as you can see, this is a straight line graph, meaning the gradient is constant. It doesn't change. Meaning the resistance stays the same, meaning the temperature remains the same. Okay, so here we can see, okay, for both of them, the gradient is constant, which means that the resistance is constant, which means the temperature is constant. Okay, and if it is constant, I must put in more lines next time. If it is constant, the temperature is constant, it remains the same, then we say that conductor is an ohmic conductor. An ohmic conductor because it obeys Ohm's law. It falls under the law, the temperature remains the same. An ohmic conductor. Okay, now, when you have a circuit, my plan was for you to play with the circuits. We will see. When we have a circuit and we connect it right, when we have that, then after a while, this will become warm, the wires will become warm, so our temperature does not stay constant. What can we do if we're busy, especially busy with an experiment like this? You see the, when we're busy with an experiment like this, how can we ensure that the temperature remains constant? Say again? No, but it will get warm. What about the resistor? What can I do to ensure that when I take my readings, that the resistance is constant throughout the experiment? Don't think too complicated. Think practical. Switch it on and off. Alright? When you want to take your reading, make sure everything is ready. You switch it on, put your switch on, take your readings, okay, and put it off again. Because the longer the circuit is going, the current is going, the warmer it will be. Okay, and that is, in grade 12, you're going to do a practical with this, and then the key thing is putting in a switch, otherwise your readings will be skewed. Okay, so in our experiment, here I want you to go up. How do we keep the temperature constant? No, not there, sorry. Temperature constant. Add switch. Not the energy drink. An actual switch. Alright. Now, if we get an ohmic conductor, then obviously we get a non-ohmic conductor. Something that does not obey Ohm's law. A non-ohmic conductor. That is one with a ratio, either 1 over R or R, does not remain constant. Okay, and we have lots of examples of that. We have a light bulb, because the light bulb becomes warm. And then as the temperature increases, the resistance increases as well. Okay, I can't pronounce it in English. It is a diode, diode probably. It's also an example of that, but it's not one that you use a lot. Let's think of examples that you use a lot in your everyday life, where the resistance does not remain constant. If Eskom is on and we have electricity. What is something that you use every day where it gets warmer or colder? Okay, wait, I'm hearing two things. Okay, yes, your charger is one. Phone, whatever. It's something that you use, actually, like your oven. Your kettle. Yes, your TV, your stove. Your toaster, if you use one. Your anything that becomes warmer. Now, I heard microwave. Have you looked inside your microwave? Is there an element?
Yes.
No, there's no element. There's nothing that gets warmer. A microwave works with waves. There's no element that gets warmer. It works with waves. So a microwave is not anything like a stove or an oven or anything like that. So a microwave is definitely not one.
What about
A geyser, yes. Your heater, if you have a heater with an element. Projector. Alright, so there's lots of non-ohmic conductors that we want it to be non-ohmic. Please, I want my heater to be non-ohmic. I want it to get warm. I want my stove to be non-ohmic. Okay, so there's good and there's bad for both. Now, a non-ohmic conductor's graph looks like this. Okay, so where you can see the gradient is not constant. Okay, right. Then page 4 and 5 again and 6 is grade 10 notes. Okay, well, I'm quickly going to go through that. Yes. Okay, so you can see there we have resistors in series. There, and there. Why? I only changed half of what I wanted to change. Okay, we can see when we want the total resistance, we just add them normally. If you look at your current, there your little mini walks, they can't split up anywhere. They can't go through the voltmeter because the resistance is too high. So there you can see the current is the same everywhere. Now, this is what I forgot to change. I wanted that to be A's. A1, A2, A3. They are all the same. The current is the same everywhere, so the ammeter readings will be the same everywhere. All right, but now we have our volts. Volts. Your energy, your sandwiches that you pack in for the day. Okay, you have to pack in for how many subjects? 1, 2, 3 subjects. Okay, so you're going to split up your sandwiches into 1, 2, 3. Okay, so you can see there the sum, what does it mean? Plus, minus, divide, plus. The sum of the potential difference over each resistor is equal to the potential difference over the whole circuit. So we say, the fancy wording is we say resistors in series is potential dividers, energy dividers, volts dividers. Okay, let's look at an example there. Alright, there you start with your 6 sandwiches and you walk You have to walk through the 2 and the 4 and the 12. So the current is the same through all of them. You have to pass through the ammeter. So we can say that the total current passes through the ammeter. Total current passes through there. Then if I look at my sandwiches, my energy, I have 6 sandwiches and I have 3 periods for the day. So I'm going to split them into 3. Not 3 equally, it doesn't have to be 2, 2, 2. Okay, we just have to split them, we'll figure out how later. Okay, then they ask you, calculate the reading on the ammeter in the circuit. Then you ask yourself, where's the ammeter? There it is. What does it measure? The total current. So for that, for the total current, I need the total resistance and the total volts. Okay, now, again, if you have extra classes somewhere else, this is not an official subscript, T. You can use it for yourself, but it's not an official one, so you don't have to. Okay, so, Butimelu, you did not answer. What is the total volts for the circuit? Fatuba, the total resistance. 8? 18. How did you get to 18? You added them all together. She said the total resistance is 2 plus 4 plus 12, and that gives you 18 ohms. Alright, then we want the current, so I start with Ohm's law. Oh, no, not that. Sorry. That is Ohm's law. Now, this is a formula on your data sheet, so you write it down exactly like it is on your data sheet. I think that's the thing I say the most in this class. And still some of you don't do it. All right, the total resistance is 18. The total volts is 6, and we want the current. Now we see, okay, the current is at the bottom of the equation. We don't like it there. What are we going to do, Bukumuso? Do you guys know the cha-cha slide?
Yeah.
Cha-cha now, y'all. Cha-cha again. And then somewhere he says, I don't know where somewhere then he says,
Slide to the left.
before that. It's yeah, crisscross. And every time I say this, that song gets stuck into my head. Crisscross. You're gonna crisscross. .33 and the unit? What does that stand for? Amperes. Amps. Alright, I think I've fried your brain enough for today. Okay, so what I want you to do now is on page 10, I want you to do question 1, 2, 3. Wait, no, not 4. Nee, wacht, let me just see what current it is. No, you can do 4. 4, 5. Okay, but the first few are very short. Very, very, very short. It's like 3-mark calculations. Okay, so go to your first few formulas that we had. We had this one and that one and this one. And you're going to use that over and over and over again. Remember, the answers are at the back there. Okay, so I'm not even going to mark it tomorrow. You do it now. You mark yourself. When you are done with the work, you put up your hand, I'll mark your book, and then you can play with the circuits in front.